Yeah, in this 10th week, we are going to talk about some other techniques of condition monitoring other than vibration analysis, which we had seen so far. And particularly, we will be discussing about how electrical motor current signature analysis can also be used for fault detection. We will talk about thermal imaging, wear debris analysis, oil analysis, and later on in the 11th week, we will talk about other NDT techniques like acoustic emission, ultrasonics, X-rays and so on. So, well, coming to this lecture on principle of motor current signature analysis, this is primarily what I will be discussing today, like what is the theory behind motor current signature analysis and why it is important and why it becomes helpful to use MCSA to find out faults in rotating machines, the associated instrumentation, and then basically I will be seeing how MCSA could be used to find out faults in gearbox, submersible pump, and perhaps we can use MCSA to find out faults in any mechanical system being driven by an electrical motor. So, as you all know by now that nearly 70% of the monitoring is usually done by vibration, and that is the statistics throughout the world. But the problem with vibration based signal analysis is sometimes we may have problem locating the transducers or mounting the transducers, in the sense I will give you an example. Imagine I have to measure the vibration of a gearbox of a wind turbine, which is perhaps 50 meters above the ground. It is not convenient humanly to monitor at such remote locations, or in other words also underground. Of course, today the technology is such that once the accelerometer or vibration transducer is permanently mounted at the location, we can have Wi-Fi or wireless transmission to transmit the signal in packets and analyze the signals at the receiver station. That is a new technique which has come up, which is aiding many of these vibration based signal analysis. We will talk about these in the future scope of machinery condition monitoring. But coming back to this slide, the other techniques are wear debris analysis, wherein the parent material composition is to be known, so that if we see the wear particle relating to the parent material, we can say that which component is wearing out. We will be discussing this later in this week. But some of the other techniques which are becoming very popular is thermography through thermal imaging, and the most important one which we are going to discuss is the motor current signature analysis, which is a very promising technique which has come up, I would say primarily because of the research we have done at IIT Kharagpur in the last 2 decades. We started somewhere in the mid 90s, and then we continued working this, and we now have a patent on using any electromagnetic device to find out the faults in a rotating machine. Okay. So, this motor current signature analysis close to exactly about 2 decades ago, we in IIT Kharagpur came across this technique, and we have developed many algorithms where MCSA can be used to find out faults in mechanical systems. So, you can go to my website or to my Google Scholar to see the relevant literature in this area for finding out faults in gearboxes, submersible pumps, So, today when people are talking about IoT of devices IoT in CBM, the technology is such that we can have a transducer, very miniature, Wi-Fi, cloud computing, wherein the transducer is remote from the machine. This is my machine. Okay. So, in the sense that anywhere we want to measure the condition of a machine, all I need to have the transistor accessing the current, and then we can transmit by Wi-Fi, and all the analysis can be done on the cloud. And that is the technology which is prevalent today. So, let me come to the theory of MCSA. Well, before that, I need to measure current. Okay. So, we can use a current transformer or a Rogowski coil, but we will talk about this Hall effect sensor, wherein suppose this is my current waveform. Okay. If there is a defect, and usually a prime mover like an electrical motor is actually driving a mechanical unit. This could be a gearbox example, or a pump, etc. But then this motor is fed with a conductor wherein I can measure IT. So, if there is any defect in this motor, in this mechanical unit, it is going to influence as a load torque on the motor. So, imagine the motor is being subjected to a load torque because of a mechanical defect. Now, if the motor is subjected to a defect which is at a different frequency than the rotational frequency, the motor current may and will get modulated. So, the key to finding out fault in MCSA is actually analyzing the modulated current drawn by the motor. Now, imagine this could be a unit very far off. This current carrying conductor could be accessible, usually a Hall effect sensor. Well, Hall effect sensor is a special semiconductor device, okay, wherein if a current carrying conductor is flowing through this Hall effect sensor, if I give a current, some current I naught, because of the magnetic field produced by this flowing current which I want to measure, I will get a voltage, and this is usually a Hall device, a semiconductor. Okay. So, this becomes very popular in the sense Hall device is somewhere kept here, and all we need to do is put a current carrying conductor through this Hall device. okay, and then we will get a voltage. So, we need to give a current. So, basically we need to have a voltage source across a resistance where I can vary the resistance so that I can nullify it. This output voltage should be 0 when there is no current. So, this arrangement can be done, and there is a knob here which can help you to calibrate the Hall effect sensor. But the essential advantage of using a Hall effect sensor that I can measure all the way from DC to about 500 hertz, and that is the current frequency. Okay. So, MCSA becomes very simple, that all I need to do for this motor is, if I put an Hall effect sensor, motor could be 100 meters away from you. We need not even walk up to the motor to put a vibration sensor. All I need to do is have access to the current carrying conductor of the motor and then access it. So, in terms of the signal analysis equipment, all I require is a data acquisition unit, because this is a very slow signal, 500 hertz. I can capture with the data acquisition unit, and I can have a standalone FFT analyzer or a laptop. So, comparatively this is a very cheap setup compared to the traditional vibration transducer. So, basically all you need to have is a computer with a data DAQ and Hall effect sensor. So, this is a very cheap method, very cost effective compared to vibration measurements, because the vibration measurement, the essential problem is inconvenience of mounting the transducer. So, this is becoming very popular, the motor current signature analysis. Okay. Now, let us look into the theory of motor current signature analysis as to why it is beneficial or why it is able to sense. Now, look at this, the torque which I discussed as TL on the electric motor. This is due to the oscillating torque due to torsional vibration. Now, what is this torsional vibration? So, this motor which I am talking about, suppose it is driving a mechanical unit, it is being given a load torque. Suppose there are, this torque is a constant component plus some T I is equal to 1 to 3. This case where T I is maybe some constant cosine 2 pi f1 t plus phi 1, where f1 is the mechanical defect frequency. So, in this diagram, say f1, f2, f3 are the 3 defect frequencies, which could be because of a gear, which could be because of a bearing, etc., etc. So, in a sense, these defects are going to give a load torque on the motor. Now, the current drawn by this motor essentially has 2 components. One is the magnetizing component, another is the torque producing component, because the current drawn by this motor will be in a particular phase magnetic plus torque. So, magnetic current will produce they will all get modulated. Okay. and they all are 90° out of phase, ISM and IST. Okay. And then I have written here ISR, ISY, ISB, because these are the 3 phases of the motor. We will discuss any one phase. So, in any particular phase, you see the magnetizing component is given by a sine function, and the torque producing component, which is 90° phase difference with the magnetizing component, is given by a cosine component. So, these are the 2 current components being drawn by the motor. Now, so in any particular phase, for example, in our phase, if I add the magnetizing component and the torque producing component, if I add them up, sine and cosine, I will come up with an expression. The total current drawn will be certain amplitude, but most important is it has terms like Fe minus F1, where Fe is the current supply frequency. For example, in our country, Fe is 50 hertz, in the United States it is 60 hertz. Well, but this is the constant current frequency which is at the supply side. So, you see this Fe minus F1 and Fe plus F1, the supply current frequency basically gets modulated, and this is the defect frequencies. In fact, this is the reason why I can measure current to detect these frequencies. So, basically all it boils down, because sidebands are there, you can pretty well say that they are modulated, because as you know, modulated signals in the spectrum will give you side bands. So, in fact, if you go back to our Google Scholar, you will see these literatures and the entire theory behind these. So, basically, now to demonstrate this motor current signature analysis on a gearbox, I am going to briefly go over an experimental setup which we did in the lab. So, this is a 3-phase 2-pole 7.5 kilometer induction motor, which is driving an 4-stage automatic gearbox, which is this gearbox is connected to a generator, which will, and because this generator is rotating, the armature is rotating, it will generate a voltage, and this could be loaded by a resistance loading. Okay. The view of the experimental setup which we have in the laboratory. So, motor, gearbox, generator and the loading unit, and you can see the Hall effect sensors here, which are measuring the currents in the 3 phases. Okay. And then this is the resistance unit, and then we have the gearbox here, right. Then automobile gearbox, where I can induce defective gears and then see the current drawn by the electric motor. So, this is just to give you an overview of the experimental setup which we did. So, this is the motor driving the gearbox, and then this the gearbox is connected to the generator, and generator has a loading unit. And because, and then in the supply side we have 3 Hall effect sensors to measure the 3 phases of the current. And then because we wanted to establish that whatever conclusions we come or obtain from the current, we also need to substantiate that or validate that with vibration measurements. So, we put a triaxial accelerometer and also an uniaxial accelerometer on the frame. We collected all these signals onto a tape recorder and analyzed them in a DAQ system, and of course, we also monitored the motor rotational speed using a photoelectric probe. So, this is the view of the gearbox, the automobile gearbox. There are the 4th gear, 3rd gear, 2nd gear. So, we operated with the 2nd gear, and then wherein we artificially removed the gear, seeded defects and put it back. So, if you look at this signal, if the supply speed is 49.1 hertz is the input shaft, and when we are running in second gear, the second gear output shaft comes out to this, and then the defective the gear meshing frequencies etc. are given here. So, when it is running at gear, the gear meshing frequency is 630 hertz, and this is how the defects in the gear look like. Which we call as D1 is one tooth removed from the gear. We use a wire cutting EDM to remove this gear, and then D2 is the removing 2 gears, and of course, D0 is no defect. So, we have 2 cases, D0 no defect in the gear, D1 is one tooth removed, and D2 is 2 teeth removed. Okay. So, all these conditions we ran the gearbox at different speeds, measured the current, measured the vibrations, and then all the conclusions which we have got. Now, another thing which you will notice here, even the frequency range is not very high, unlike if you have to find out the faults in bearings or gearboxes where we had to have a higher frequency range. It is not required in monitoring current signatures. 0 to 2 kilohertz is good enough. We sampled at 4.096 kilohertz. The total time record was 2 seconds. The gearbox was run at different load conditions, 0 kilowatt, and these kilowatts 1.875 till 5.625, because in the resistance unit there were units where we could switch in the circuits or resistances to introduce the gears. So, once this signal has been acquired from the DAQ system into my computer, I need to do some sort of an analysis. The conventional FFT analysis, sometimes it becomes problematic because of the low signal to noise ratio, and then we may not be able to capture these signals. But if we do demodulate the signals, we can very easily calculate and identify the defect frequencies, and if there are transients, as if the gearbox or the mechanical unit is not running at constant speed, we could use some of the non-stationary signal analysis techniques as well. But this is the case wherein we see FFT analysis and amplitude demodulation from 0 to 100 hertz. So, this is the vibration signal obtained from this gearbox, wherein I can see all the input frequencies, and that is what is expected. Okay. But when we first time did our analysis, okay, we were excited to see that the sidebands around the supply frequency, Fe is 50 hertz is the supply frequency, I can see these peaks. Okay. And then if we do these are the modulations, okay, sidebands are there. So, if I demodulate the amplitude modulated signal, I can very easily see F1, F2, F3, and if the severity of the defect increases, these amplitudes of these frequencies would increase, and that is the telltale sign that a defect has occurred. So, we did this with D1 defect, where there is one teeth removed. We did this with D2 defect, and then of course, we did this with many high frequencies, wherein for the frequency modulated signal, if there is any speed fluctuation, we could see the gear meshing around certain order of the gear meshing frequencies, okay, because the GMF is very high. So, GMF is RPM times number of teeth. If the speed changes, the GMF would change, okay, and then the GMF plus minus Fe was also visible, and these are usually high frequencies. Okay. So, just a summary of the vibration and current signatures. To monitor vibrations, input gear shaft frequencies from vibration frequencies can be measured. Gear meshing frequencies need to be monitored. So, we did that with the input shaft, the gear meshing frequency, and the supply frequency. Okay. Of course, with load, the supply current amplitude will also change. So, if you see in terms of the milliampere, the variations in the sidebands for the defect gears with the severity of the defects, they would increase. Okay. FM2 plus minus Fe and then 13 Fe, okay, these frequencies would show up. So, if there is transients, the current would change, and then this can be done through non-stationary signal analysis. So, a complete strategy for monitoring the gearbox faults is given in this chart here, and the details you can find in our. Okay. The similar thing which we did for the submersible pump also, where we removed artificially the vanes, and then this was done at different impeller conditions. Similarly, supply frequency, speed controller and the Hall effect sensor will measuring the analysis. Okay. And then we can see the current spectra at 40 hertz supply frequency, there will be lot of sidebands because of the broken bar impeller. So, again by monitoring the severity of the defect increases with the height of the sideband increases. So, this could be done. So, immediate use to the Indian industry is, because MCSA is remotely we can use them in submersible pumps, reactor cooling pumps inside nuclear reactor in rolling mills, in large reduction gearboxes in gas turbines, power plants, and even today in electric drive vehicles. Okay. So, more of these you can find in my book, and particularly if you go to our website, you will see many of these conditions there and the literature, associated literature. Thank you.